Hi, my name is Adrian, and we'll take a quick overview on how I've made Boid setup in Thinking Particles 4. I was planning to do this a long time ago, but didn't have time to do this, and now is the right time, I think, because I have some free time. So sorry for the delay. Also, now I'm YouTube partner, and I think from now on I'll try to make more higher quality tutorials. So let's start. So this Boid setup I was doing for a company via that I am working, and it's based on simple Boids rules like grouping together and like velocity towards center, matching velocity, and keeping a distance from each other. Also additional conditions like avoid obstacles, some random movement, and external forces. And also follow an object. In this example, the object is a point which follows a path. So let's play and see what we have now. You can see that they're trying to avoid the torus. Those objects are not avoidable, just the torus for now. Okay, so we can increase the number of Boids, like let's say 100. We have more Boids. We can also remove goals, number of goals. In this case it's not working. I didn't finish it, so the easiest way to do in this setup is just to disable the following condition. Okay, tendency goal. So there was a little bug where you cannot press play after changing some settings in Thinking Particles. So now they just flying randomly in the world till they hit the boundaries. Those two points represent the bounding box where they can fly. They have some smooth collision, so after they hit the box, they will not just like bounce around, but they will smoothly return because it's a zone of influence. Okay, so let's play a little bit with settings to see what those settings does. Also, I didn't play with this setup for a long time. I think it's almost half of a year or even a year. So I hope I remember all the settings. About the following, let's see. I've disabled the follow rule, tendency goal, but I remembered that I have a setting for this one. Yes. So let's see. The speed to neighbor division is a divisor which divides the length between two Boids, and use this length as this vector as speed, additional speed. So let's see. So we have, for example, two Boids, and the vector between. So we're now processing this Boid. So this will be 1, this will be 2. So we have a vector from this to this one, to neighbor Boid, and the division setting divides this vector in small segments, and it will use this segment to add, for example, let's say this number of segments, and after it will divide, it will add to the current velocity of the particles. So if particle velocity is this, it will add this segment of the velocity, like so, and we have a new velocity vector. So it will have a tendency to go towards the nearby particle. So after a certain amount of time, it will rotate it more toward this particle at each frame. Okay, so let's see. Next setting is let's before going to next setting, let's see what influence has the first one. So if we'll decrease this one, it will go faster to near to neighbor. So let's set it to 5. And if we look now, it should format clusters of Boids, because they have a bigger influence to our neighbor, and they'll divide in like groups. Okay, we can increase it even more, like say 1. So now at 1 it will use as velocity the same distance between them. So you see this is not so realistic motion, but we have some results. Let's set it back to 50. Next, next we have search distance. So search distance is the radius which Boids will see each other. Now it's set to 100. Let's play and see the current animation. You see that they are not so influenced between each other, because they go in different direction and not form a big group. If we'll increase, by the way, increasing this value also increase the processing time, because it will process more particles for each one. For each particle it will get more neighborhoods that needs to be processed. So let's increase it to 500, like so. Let's see what we have. So you see now they're forming a bigger group, because now they all know about existence or are influenced by a more distant neighbor, like so. So let's set it back to 100. Now we have follow divisor. So it's the same as speed to neighbor division, but it will affect the following target, like for example this null object. So let's set back follow on, go to this frame, and we see that she's now very lazy movement. They have lazy movement toward the target. But if we will decrease this, let's say to 10 times lower, they'll go much faster. But there is also one problem, because if they reach it very fast, they will go in front of it. So it's maybe not what you want. Like so. Let's set it back to 100. Next we have angle of view. This is not it's not a standard way to make Boids, but actually it's not a part of standard rules like the free rules of Boids, but it's an additional thing that add realism to Boids. It's because Boids are living things and they have eyes, and each one of them have a kind of field of view, so they may not interact with each other in free space, but only the frustum that they have, they see. So I've added this option too, but I don't use it because it may create groups that don't interact with each other because they don't see each other. So it's now set to 180 degrees. So let's say if we have two particles, Boids, and this one is oriented in this direction, so we have like let's say 90 degrees in this setting, but 90 degrees in this setting is like 180 in real. It's like one side degrees on one side, so it has always field of view, and it sees this particle, but this one below, but it doesn't see this this Boid instance below, because it doesn't enter this field of view. Having 180 degrees of field of view, it will have a circular field of view, 360 degrees, and it will see all the particles around it. So this is what this setting does. So let's decrease it and see what happens. Let's set it to 45. Let's remove follow. Let's also increase search distance. Okay, so you see, first time when we increased the search distance, we created some kind of sphere or ellipse, but now we're kind of creating a directional groups, because they don't see each other, the backside of each other. So if we increase a little bit, let's say 90 degrees, it will be it will half the space, so 180 degrees. It will not see just the back of the backside of each other. So now it should create like two directional groups. Yes, so we have like two directional groups. Those one are just had a different direction, and now they're separated each other, but the main groups are those two. Okay, so you with 180 to interact, it will create one group in this radius. Okay, you can see that they interacted with each other. So let's set it back to 100 search distance. Next we have velocity matching divisor. It's same as speed to neighbor divisor, except it will average the velocities of neighbor boys. So it will get the average. So let's see. We have two boys. Okay, so we have two boys. They have different velocity, and if we transfer so this is the first one, this is the second one, so this is the one that we are processing. So if we transfer this velocity to this one in this Boids space, and what this division does, it takes the two vectors and segments them in using this setting right here, velocity match divisor, and it will slowly go towards this velocity. So on each frame it will be influenced. So this particle will slowly go in this direction. It's not the best way to do. Matching velocity will be better with quaternion, so having a spherical interpolation rather than linear. So we'll have something like this. So you will interpolate direction with quaternation, but I don't want only direction, I want also the speed. So using linear interpolation will also interpolate the speed. Okay, so let's see what we have next. Distance to neighbor. This setting is for keep apart rule. So this is the distance that boys must keep away from each other. So like intimate zone, if I express this correctly. So let's see if we increase this. Now they should be more spread around. Yeah. But with also let's increase the search distance to see it more in effect. Okay, so you see now instead of just going having a larger density, they will be more spread around, even if they interact with each other, because the force acting on separating each Boids have a bigger impact because of the bigger radius they need to hold from each other. So if we decrease this value, let's see, let's say to 10, we'll now create they'll be very near each other, like here, you see. And also this is a bad idea, because it will depending on what geometry you have, it will have interpenetration geometrical. So you might want to get a good radius for this, to also keep it real and also don't have intercollision Next, let's put it back to 50. Random multiplier is another force which is not a standard one, but it adds a random directional velocity to each Boid to get more chaotic movement. Like, let's see if it should be visible. You see that they move like randomly and gets something like a fish move. Also they are animated, so I hope you see the movement. You see that she's going like up down like this one. See, they change the direction, and this is the random force, but I want to control it with a multiplier, so I can set it to 100, and now they should be like more randomly moved around and influenced more by this force. So you see it's more chaotic and they have a bigger velocity. So this is not influence over only the direction, but also speed too. So it's additive. We can increase it even more. So there are now like atoms, electrons moving around. So okay, so is not what we want. We want a smaller random movement. So if we decrease it to 0, let's see, it will be less realistic. You see that they just follow the standard rules, moving each other. It depends on your preferences, if you want a random movement or not. Okay, so let's put it back. So keep distance divisor is the same thing as speed toward neighbor division, except this is for keep apart, so it's the force away from each other. So let's see, if you have two Boids, like so, the keep apart force will be, let's say we processed this Boid, and we have this vector towards the next the neighbor Boid that we are processing. So to keep it apart from this one, we'll inverse the directional vector towards the neighbor Boid. So we have this vector. Actually it will be the same length. Also it has a velocity of its own, and having this division, we divide this difference between each other, between each vector, and have a small influence on each frame to make it go away. So this Boid also go in a different direction, and make it so they will not collide with each other. So we can, if we will put this force too big, it will snap really fast, and also put them a big impulse on when they will have a smaller radius between each other, and we don't want this to be. We want a smooth influence. Each other. We also don't want it to be too small, and so they will be too close, and also very dense if it will be too small. So If we increase this or decrease this, if we will decrease this, it will have a bigger impulse on them. So get away, you're too near me, very near me. So you have a small radius which I've set here, distance to neighbor, this one. So if we will increase it, you can see that the force which makes them group together is bigger than the one which repulses them and make them collide with each other. Okay, so let's set it back. By the way, let's to represent it better, let's increase again the search distance. So okay, so this is with 2. You see that way try to go away. So let's set it to 200. Now we're not aware of each our collision radius, like a sphere around each other. So they just interpenetrate each other. So if we decrease this, you can see that they really hit each other in face and create a big vector of repulsion. Okay, so let's set it back to 2. Next we have align laziness. So in order to not have after all these forces are applied, we get a new vector, so a directional vector to move. So in order to not make this look very snappy when the Boid orientates around that new vector, we can set a laziness, align laziness to the new vector, so it will have a smoother rotation. So if we set this to 0, let's set this to 100. If we set this to 0, now it should snap very fast to new vector. You see, like it's changing instantly the direction. But if you set this to 1, it will be more smoothly. Or maybe let's see, I don't remember how I connected it. I think if 1 is more smoothly and 0 is faster, is instant snap. Okay, let's test it with bigger search distance, because it will have a more interaction. And let's set it to 0. Let's see. Yeah, so yeah, I believe at 0 very snappy, and let's see at 1. Yeah, so the bigger the laziness, the less rotation interpolation they will get. So lower will snap them. So I found that 0.75 is the best value, best interpolation value. Next we have max speed. Max speed is simple, just a clump of the speed, so it's get higher than this value, it will be rounded to this value. In this case, if 300. Next we have random chance. Random chance is basically the chance that you'll get a random direction, which is influenced by that random multiplier. So in this case is 40%. Next we have number of Boids. Here is 200, it's just the number of Boids. Also number of goals. This is the number of goals that it will follow. Currently we didn't assign any goal, but let's see, we have this point here which is following the path. So if we enable follow, we see that the Boids will follow this point. So let's add another point. So we'll pick this point here. So we need to set it to goals group, object to particles. Like so. And now if we play it, we see that they divide each other into parts. Yeah, you see it, they are a little chaotical. Not sure what is the problem, but you'll see. We'll try to see later. Maybe because they're influenced by. So I'm not sure I had this problem, but I didn't need true goals, so I kind of left it in there. We'll have a look later when we'll look at the setup. So let's remove this point. Next we have the avoidance objects. In this case I have this torus. You can see that they avoid colliding it by changing their direction. So let's create a new object and set it to avoid it. Put it in their way, like so. And let's go to thinking particles and pick this sphere, and let's set it to avoid object group, object particles, and instance shape. Okay. Now let's play. So now we see that they avoid torus and also they avoid our sphere. So this is all in the interface, except we have also the force field, which in this case I have a wind, and it also throws some random movement, but in a more group fashion, like because the turbulence is a field and it has a smooth randomness. So it will affect group of particles, you see, like waves of particles, not just random per particle. Okay, so let's, if we increase this salvage, it get bigger influence, so on. So let's see the setup. Okay, so we have, let's collapse this, and we see that we have some float values, which was initially values that I used internally in thinking particles to set for the settings. but I later changed this to external interface, so you see the connections, and I left them just so I have a default value which I know they are working and not start from scratch. So they're now just for reference. All the values are not connecting to the external interface in modifier panel. Okay, so next we have our groups. The first one is Boids inits. The Boids inits is for initting all the values and creating all the objects that we need. So first one is create Boids. It's just using position board. In this case, a volume position. It's a box which generates the fish in their volume. I use a node operator and volume pose to generate them. Also, the position board has pistol shot settings, so the shot amount is connected to external number of Boids. Lifespan is a big one because I don't want them to die. Also, I have an initial speed of a small one and random direction to have some more random size and so on. So we set the initial alignment to the direction of travel. Also, we init the memory with the default values, which are just all zeros. So we have average position 0, average velocity 0, number of neighborhoods 0, and also it's not hit. It doesn't hit anything at the beginning. So 0.3, boolean, and integer. Okay. So I didn't name it right. I set it to average position and average velocity, but because I divide later, it's the sum of position and sum of velocity, which I store in them. Let's rename them correctly. So sum positions, sum velocities, like so. Next we have init avoidance objects. It's also object to particle, and it's a TD tool, so it's exposed to external modifier panel. Also we have object particles for goals, also exposed. So if you want to see how TD tools are made, look into Seba's documentation on thinking particles. It's not that hard, but you may see some other interesting basic things that you may want to know. Next we have assign goals. What it does, it loops through each pair of particle or Boid in group, and it has a random chance to get into the group. The random chances basically depends on the number of goals. So if you have 2 goals, it's 50%, if 3, 33%, and so on. So you have this threshold which selects them, and we have one which we divide but by number of goals to get the percentage which the coefficient which we want to select the particles into group. And if we set the reference to our goal, also we want to move them to a new group, so we not loop over them again and so on. So you see, we move them to group Boids. Initially they have another group, newborns. Also we use that threshold for number of Boids, number of goals. If the number of goals is 0, we just send them to that group. We don't need to set a ref or something else. So we see the initial group are newborns. So move group Boids. So next we have the particles which left after the previous group, dynamic group, because we selected randomly. There are some particles which didn't get a new group, so we set it to the first group we found, set a reference to move to the new group. All the particles were left there. Also around here might be the problem that they get some chaotic movement incorrect, but not sure what the problem looks correct to me. So next we have void forces. This is where we apply all the forces which they interact with each other. So let's collapse those. First we have a pre-computation. In pre-computation we we calculate all the values like average, so on. First we reset the values all to 0, like some velocity, some position, so on. Next we calculate the averages by looping through two pairs of Boids, and depending on field of view. This is where we use the angle view. We select, we process only those particles in field of view. We also have a distance input from the external interface. So we have this expression here, which checks if it's in field of view. Let me select it and show you. So we have unit vector of velocity and unit vector of toward neighbor. We use dot product to get the cosinus of the angle between them, and then we call our cosinus to get the angle between them. We also make it absolute, so we get absolute value, and we check if it's less than the angle, less than the angle we need, and we will output 1, else we will output 0, or boolean, true or false. Like so. So let's see. We take the particle velocity, the particle A, and we have two positions, particle A and B. So we use the difference between the B minus 1 particle, and so we get the velocity vector towards the neighbor particles. Yes, so this is velocity. So let's draw how how it's looking, how it's working. So we have velocity vector. We have a neighbor particle. So this is the vector towards the neighbor particles. It doesn't matter which velocity it has. So this is the field of view, and we check if it's in the field of view. We process it. So the difference of their position is to create this vector. So this is the first particle we processed, and the second one is the neighbor. Okay, so also we check if particle IDs are different. We don't want to process same particles again. So this is our inputs, some position, some velocities, number of neighbor. This angle of view is just a proxy to have a different curve. It doesn't do nothing, it just takes the input from outside. Okay, so this is the output memory. So let me write a pseudocode how it's working. So for each pair of particles A, B, if particle A sees the particle B using this angle that was set in modifier panel in settings, then we add, so let's see, position, okay, only if they're in field of view and doesn't have the same ID. So we add the position, neighbor position, and we add the neighbor velocity, and also add 1 to the number the count of neighbor. Okay, so if A, C, B, and using the angle view, add to A memory variable of some position, I add to some position of A the neighborhood position. It will look like A dot some position equals A some position plus B position, and A some velocity equals A velocity some velocity plus B velocity, and A dot num neighborhood count equals a dot number of neighbor plus 1. Okay. Let's see. Next, we after pre-computation we have a tendency goal force, which just takes pair of just take our Boids reference goal and position and interpolates towards it using the position difference and adding to velocity of our Boids. So this operator is adding two vectors, and we write it to particle data. So this is the goal, the red dot is the goal, and black is our particles. So we get the vector towards our goal. And we so if we add the two position and divide it by 2, we get the middle. If by 4 we get the 1/4 of the distance. So we get the segment of velocity, and we add it to our velocity, so each frame it will lean toward the goal. Okay. So we write this to particle data because if I don't use velocity, because velocity is an additional layer, so I cannot read in a different dynamic operator till next frame, but because I need to operate instantly with set and get velocity, I use particle data because it's instantly sets the value without waiting to add all the velocities and so on. So next we have random C. It just creates a random vector by using three random numbers for x, y, and z, and multiplying by a random multiplier, and adds to our velocity using a random chance. So we have this random and threshold, which is feed with our chance or options from outside the external interface, and we set it to particle data. Next we have fly towards central rule, first rule of Boids. So it's we get our sum positions, a number of neighborhoods, and we divide sum positions to get the middle position of our neighbors of our group, which we see. So also I check if the number of neighbors is 0. I don't want to divide by 0. Even if it will work okay, I don't like to do it. So we also divide by our divisor from outside to get a smaller interpolation or faster interpolation. Okay, so it's working same as the goal. Instead of goal is just the neighbor Boid. So also we check the threshold if the number counts is 0, of number of neighbors is 0. We don't want to process it, and we add to our velocity the segment that is calculated. so it slowly will go toward a neighbor, center of neighbors. Next we have keep apart rule, which keeps the voids apart from each other. We loop through each pair, and we have some interpolation, radius interpolation, because we don't want to have a big impulse on if the particle is less than the radius of interaction. Is not the neighbor radius, but the radius which a neighborhood can get closer. So intim radius. So we have this interpolation formula. If the neighbor Boids gets in the middle, it will get only a middle of the force we set in the settings, a half of force. Repulsion force. If it's in the center, in the same position we are, we want a full force to reject it, to repulse it instantly. If it's at the edge, it will be 0. So we don't have any influence on that. So we get this gradient of interaction. So it's much better than just having a direct impulse when it's lower than this radius, like you find on some most of tutorials on the internet. I prefer this method because it's more smooth. So yes, we have our distance divider in this formula, expression for interpolation, and we add this through our velocity. We also have this expression to keep not the same ideas, so we not apply them ourselves to condition. So let's see, next we have match velocity. Match velocity is a rule which will try to match the same velocity as our neighbors. So we take, it's almost the same as positions, just with velocities. Sorry, so we have two velocities which get interpolated by divisor, which was set in external interface. Yes, so we get some velocity divided by number of neighbors. Also we check if threshold to not have 0 neighbors, and the result velocity which is interpolated is added through our velocity. So this is the division. So we subtract from the neighbor velocity our velocity to get the difference, and then divide it by division, then add it to our velocity. In this, okay, this I have two particle data. It's redundant, but just to keep it clear. One on the upper part and one on the lower part. It's doing the same thing. Okay, threshold. Do not apply it to the same particle. Next we have speed limit. Just checks if the speed is greater than our max speed. It just takes the unit vector of our velocity and multiplies by max speed, or just outputs the current speed. Also have external force, which in this case is just wind. It's also exposed through external interface, which is binded with space warp binding tool. Next, the avoid of obstacle I will talk about later a little bit, because it's a little bigger topic to talk about. Let's finish first with simple rules. So boundary rules is not that hard, but how it looks. We just have a minimum and maximum position. I use two points in scene, so we have minimum and maximum, which creates a box. So having these values, we can create imaginary boundaries, and also I've used a smooth expression, so it will not just bounce on the wall, you know. It will smoothly it will have a smooth repulsion on the edge of the wall. So instead of having a ping pong repulsion, it will all have a thickness, which gets a gradient of force which applied through repulsion. So when it's at the edge, it will get 100% of repulsion. When it's on the effect range, it gets 0, and when it's the middle of the thickness box of this interval, it gets half of repulsion. So we get this curve, nice curve of particle movement instead of direct repulsion. So you look at this expression and you get the scene and how it's done. So you have an interpolation distance, which thickness. So we have minimum and maximum. Also there are two formulas, one for the minimum, one for maximum. It's the same but have a different signs. So I have 3 clones of same expression for x, y, and z, and same for maximum. It's 3 formulas. Okay, so not this one, the maximum expression. Yes. You can see it, which this is the expression for the maximum and one for the minimum. So let's see. So after that it's adding same to velocity, the result velocity is adding to our current velocity and outputs to our particle data. Next we have Boids advance, which just sets the alignment with laziness from our setting. It just rotates toward our velocity, and geom instance, which has the fish geometry with animation. And also debug, but I debug the values of velocity, position, so on. and this is cache, where I throw it for the cache when I want to cache it. Okay, so now let's have a look at our avoid obstacle dynamic group. So how it's working. So let's say we have our Boid and a sphere. So what we're doing, we're shooting a ray, and this is velocity of a Boid. So we're shooting a ray in the direction of velocity, the same length as velocity, but you can multiply it by 2 or 1.5, for example, to get it a little forward. So we use, this is 1.5. I use the same as velocity vector. So if it hits a sphere, then let's say we see the same thing from behind. So this is the camera that we see. So this is our Boid from behind, the same position, and the ray is just a dot from this viewpoint. And what we are doing, we're shooting some rays in a circle. So you have first radius. So we shoot some rays in these directions. So we generate these points in a circle fashion, and we shoot rays in those directions. And we see if we hit the sphere, then we increase the radius, and we create another array of points that we use as ray directions and length and magnitude. So we again shoot in this direction and see if it hits the sphere. If it hits, we increase the radius, and if we get a dot which a vector which doesn't hit the sphere, then we change the direction of our Boid in the direction of that vector to avoid the collision. So from this perspective it will look like this. So we change our direction to avoid the collision. So first we check the first intersection. For optimization we don't want to always check the circles, we just have a hit flag from memory, and with intersect operator we check a vector of our velocity if it hits some obstacles. We also use a pass AB to check the pairs of our Boids and avoid objects. We check all of them without distance, but the ES is better without distance because the radius of object can be bigger. So this is the float you want to use if you want to have to multiply the velocity vector a little bigger, to, like I showed, to be like 2 times reaction forward, or 1.5, to get it react faster than the velocity vector. So 1 frame before the hitting. Actually it's not 1 frame, it's 30 frames per second, and the velocity vector is for 1 second. So we create this vector by using the position, direction is the velocity, speed is velocity magnitude, and we check for use particle shape of our object to hit, and if it intersects we set the hit flag and hit what object it hits as a reference, and set it in memory so it will not check again. Next we have check for exit, where we iterate. We have 2 iterators, one for radius of circle. So you have 5 circles that you generate, And one iterator we have for point array on the circles. We have 30 points. So we check the matrix of the Boids alignment. So have x direction, y direction, and z direction. This is for transforming the circle that we generate in the Boid space. So I use this expression to transform this, to create the circle and transform it in Boid space using the you know that to get a point on a circle you get for x you get the sign of angle multiplied by radius and multiplied by x-axis of the space you want to transform it plus y cosinus of angle multiplied by radius and multiplied by y-axis. Also for the z-axis I multiplied it with 3 just to get the circle a little forward so the rays will not go to the sides but have a direction, like if it's this the Boid. So I don't want the circle to be the same position but it a little bit forward, so to get the rays forward and not on the sides. So if it intersects something, it will loop again to the next iteration. If not, it will set the hit flag to false and it will not loop again. Also it will set the new direction using the velocity operation operator. Sorry. Okay, so next we clear the flag, so the next time we check it, we have everything cleared out. So this is the setup. The tutorial, sorry for the voiceover because my mic decided to mute for a while, make some strange noises, and I had to overdub the recording. Hope is not a big problem because I see that they're not so synchronized with the movement, and of course this happens as soon as I say that I want to make a bigger quality on the videos. Hope to fix this microphone or make it better. I'll share the scene so you can investigate and try your own settings and see how it's working. Hope you liked this tutorial. It's more of overview than how to build tutorial. And thank you for watching. If you have some question, leave it in the comments. About Boids rules you can get internet using Google, like Boid tutorials, and you see some simple tutorials on how Boid system works and simple rules. Okay, thank you for watching and goodbye. See you next time.